let's get started. Otherwise, we'll never get to lunch on time. So, yesterday, I showed you in all right. Yesterday, in the performance analysis, we ran the code, and the binary search trees performed very well on the random trees. But if you insert everything into the tree in sorted order, it ran really slow. And that's because the tree became very unbalanced. So we want balanced binary search trees. And as you recall, in the previous day's lecture, I showed the basic way you balance a tree. And this goes back about 56 years to Adelson, Bielski, and Landis with their AVL trees. It's a rotation. So we can take this subtree with its I and L and sort of swap around the I and L, leaving their subtrees roughly in place. So that's a left rotation. That didn't actually decrease the depth of the tree any. But now we can do a right rotation on this L and R, swap them around, leaving their subtrees, basically I, M, and S, in place. And now the height of the tree has decreased. So the idea of balanced binary search trees is that by using rotations, sometimes two rotations together, we can locally decrease the height of the tree. Oops. And so there's several versions of balanced binary search trees. There's AVL trees, there's 2-3 trees, there's B trees that are the generalization of 2-3 trees. There's red-black trees, which are really just an alternate variant of 2-3 trees. And I'll show you red-black trees. So what we do is we color each node of the tree with the color red or the color black. The patterns of the red and black are going to guarantee that the height is order log n, basically no more than twice log n. And here are the properties. So every node is either red or black. Every leaf is black. So these slides were meant for, old-fashioned imperative programming, but my leaves are capital E. So those can be considered black. If a node is red, then its children are black. So you can't have two red nodes in a row on any path from the root to a leaf. Okay? And so that's condition 3. Condition 4 is every path from the root to a leaf contains the same number of black nodes. In fact, from any point in the tree, every path from that node to a leaf will contain the same number of black nodes. The root is always black. Okay, so if we look at just the black nodes and pretend the red nodes aren't there, we get a complete binary tree of a certain height. And then when we insert red nodes, but never two in a row, there are some paths that may become up to twice as long, but there will never be some path that is more than twice as long from the root to the leaf than some other path from the root to the leaf. Okay, so I'm going to skip through this pretty fast. So here are some properties, right? A height h node has black height greater than or equal to h over 2, where black height is the count of the number of black nodes from the root to that point. So let's do some pictures. Here's a binary search tree. And we could color that tree with red 12. And now all the properties hold. Every red node has both children black. And every path from the root to a leaf has the same number of black nodes. Now, if we insert 8 into this tree, well, it has to go to the right of 7. It has to go to the left of 9. So we insert 8. It has to have 2 children that are leaves. The leaves have to be black. What color should 8 be? Well, we can color it red, and all the invariants hold. So that's good. Let's insert 11. It has to go to the right of 7. Has to go to the right of 9. It has to go to the left of 12. There it is. It has black children because the children are leaves. What color can it be? Well, we can't color it black because then there would be a longer path of black nodes from the root to the children of 11 than to the children of something else. And we can't color it red because then there would be 2 red nodes in a row. So we're stuck. So we could recolor. How do we recolor? We could recolor 12 black instead of red. And now everything works, I think. Yes. All right, let's insert 10. It has to go to the right of 7. It has to go to the right of 9, to the left of 12, to the left of 11. There's the 10. It can't be black because that would make one of the black paths too long. 2 of them. It can't be red because there's 2 red nodes in a row. So we can't, there's no recoloring of this tree that will work. So we can do a rotation. And so, I showed you rotations. You can take this tree with A, B, C, and X and Y, and do a rotate right to get to X over Y, or rotate left to get to Y over X. It preserves the search tree property. If X is less than Y, then the left tree is fine and the right tree is fine. So if we take this tree and rotate it left about 9, so we're going to rotate it left, with the 9 and the 12. So now it's the 12 and the 9. And so now when we insert into a red-black tree, we try coloring the node red, but if that leaves 2 reds in a node, 2 red nodes in a row, and it can't be fixed by a local recoloring into black, we're going to do a local rotation. Okay? And here's the C code. You don't really want to look at the C code. All right. So, yes?
Does the rotation preserve the red-black property?
Well, the rotation, you do 1 or 2 local rotations, and it's guaranteed that you'll be able to recolor those local nodes to satisfy the red-black property, or you may have to propagate some changes up towards the root, I think. Yes. So let's do this example. We've inserted this node X, with a B in it, but that led to 2 red nodes in a row. So we can, We recolor A to be black and C to be red, but that means we need to be recoloring D to be black. And in some cases, we may need to do a rotate. So I'm going to skip all the cases. There's lots of cases, and I will show you a different presentation. Now, one thing about, if you look up red-black trees in the literature, you find heavily imperative, update the tree in place, swap the pointers around presentations. And 20 years ago, Chris Okazaki, who was then a graduate student at Carnegie Mellon, is now a professor at West Point, said, let's do red-black trees in a purely functional style so that the insertion into the tree doesn't modify anything, it merely creates new nodes. And so, as with any kind of binary tree, if you insert functionally a new node at some depth, you have to copy the log n, we hope, nodes on the path from the root to that node. And then the local rotations can also be expressed as create some new nodes that point at the existing subtrees. So that's the framework of, what am I doing here? Of Okazaki's presentation. And so here is basically, oops, what happened? Great. Is that better? All right. So here's basically Okasaki's presentation, but translated into Coq from whatever functional language he had it in. We have a tree type, just as before, with a leaf E and a node T. T is just as it was in the ordinary search trees, except there's an extra field called color. The lookup function ignores the colors. That's the nice thing about red-black trees, that the colors don't matter to a lookup, so we just do the less than tests that we did before. And now the insert function, the insert function is much like it was before. To insert X in the leaf, you just make a node with two children that are leaves. The color of the node should be red, at least for the time being, and it has the key X. And to insert X into a tree T with with a color C, a left child A, a right child B, and a key Y. All right, well, if X is less than Y, then make a node with color C, and the left child will be insert X in A, the key will still be Y, and the right child will be B. Okay? Except that then we do this operation to rebalance this node. Okay? And I'll show you balance in a minute. If Y is less than X, so if X is greater than Y, if X is greater than Y, it has to go in the right, so we insert X in the right. This gives us a new subtree, and then we make a new T node with A and Y and their new right tree, and then we rebalance the new tree node. And finally, if X equals Y, we just replace, we make a new tree node just like the old one, except with Vx instead of Vy. And it doesn't need any rebalancing because it was already balanced. So here's the balance function. So what does balance do? It takes a color. It's like we're making this new tree node with the left child T1, the right child T2, the key K, right, and color RB, and say, make an equivalent tree to this tree node, except one that's properly balanced. Okay? Well, if the new tree node is red, then it's fine. Why does this work? So if it's a red node, leave it alone. Just wrap the T constructor around this information. If it's a black node, which is this case, then look at the subtree, the left subtree, T1. If it's got two red nodes in a row going left, then we're going to do this rotation. Okay? So the the two nodes have in order subtree A, key X, subtree B, key Y, and subtree C. And so the rotated node will also have A, X, B, Y. What are we doing? C. So T1 had A, X, B, Y, C, and then that was within this bigger tree that T1 was the left child of. So it continues with K and T2. And so this is a rotation of the nodes, the parent node T1 and T2, with T2 still on the right, but now we have a red with two black nodes. Okay, so you can see there's an implicit T that was right here. That was the tree we're really producing the appropriate rotation of. Okay, suppose T1 was two red nodes in a row the other way, in the right-hand child, then we do this other rotation. And what if T1 was some arbitrary thing? Let's look at T2. Well, some arbitrary thing. Maybe a black node. Right. So let's look at T2 now. And if T2 has two red nodes in a row, then do this other rotation, and so on and so forth. Now, the great thing about proving a program correct in a machine-checked proof assistant, when the program is already correct, is you don't have to understand it. You don't have to understand the program or why it's correct. You're just going to turn the crank and not think too hard. Okay? So you notice there are a lot of hairy cases here. If you look at the deletion algorithm for red-black trees, it's even worse. It's famously a lot of horrible case analysis. All right? This is the balance function. And we're going to prove that the red-black trees satisfy the appropriate abstraction relations, so we can prove lookup relate and insert relate and all that stuff. Okay? So let's proceed. Okay? So that's this function ints. Ints ends up propagating up the two reds in a row. Okay? If you have two reds in a row here, then the rebalancing might push it up so there's two reds in a row here and then two reds in a row here. And sometimes you get to the very top of the tree and there's two reds in a row. But at the root, if you have a red node, you can just make it black. And so sometimes, and what happens when you're making the root black when it was red? It means you've sort of increased the total height of the tree. That doesn't happen very often, right? The tree has to double in its number of nodes, approximately speaking, before you tend to have to actually recolor the root from red to black. Anyway, we have this function. So the insert function overall, this one, is run this recursive function ints and then do make black, which just is this function. It takes a tree node of arbitrary color and returns a tree node just like it, but that is black. All right, so that's red-black trees. The program is hairy. It's not obvious that it's correct. It is correct, but it's not obvious that it's correct. And I could wave my hands and argue for a long time and eventually convince you that it's correct, but it would be some horrible case analysis. Okay, so here's a little lemma that we will need in the later proofs, that if you insert a key into a tree, the resulting tree is not a leaf. Who believes that? Yeah, seems true enough. If you insert a key into a tree, it can't be a leaf. And it's going to rely on this other lemma right here, t not equal to e, which says that a node is not equal to a leaf, which is very easily proved just by inversion, of course. Okay, so let's...
Question.
Yes?
Since it's so easy to prove just using inversion, why bother breaking it out as a lemma?
We'll see. I mean, yeah, we don't need to break it out as a lemma, but let's just get there when we get there. Let's do this proof. We're trying to prove that, let's do intros. We're trying to prove that insert x vx in the tree S is not equal to E. So step one, let's destruct S and simplify. And here we'll just apply t not equal to E. That was easy. And here's the more interesting case. That big thing is not a leaf. Well, I will give you this hint. It doesn't matter whether that highlighted node, the insert x vx s1, is a node or a leaf. It's still not going to be equal to E. So I'm going to abstract over that int x vx s1 as follows. Remember int x vx s1 as a1, and then clear heq a1, like so. And I'm also going to unfold this balance function. And so now here is the thing we have to prove. Why is it so long? The balance function I showed you fit on one screen. And the answer is that when you do pattern matching with underscores in Calc, well, what it's really doing is each of those cases nested, right? So there are a lot of cases here. And are we sure that in every damned one of them, it's not a leaf? Yeah, it seems like that's true. So let's prove it by case analysis. All right? So I'm going to destruct this LTB-XK. Normally, you would not just destruct LTB-XK because you'd want to know whether it really was less or greater. You need to remember the equation for this LTB, or do a B-destruct, which uses reflection to remember a similar equation for you. But actually, we're going to just do destruct because we don't care. So now we have two cases. Well, okay, we still got a pattern match, so let's destruct C. And now we can apply t not equal to E. And, well, there's a pattern match here. So it's a match on A1. So let's do case analysis on A1. Let's destruct A1. We've got another pattern match on S2. So let's destruct S2. And now this case we can prove with t not equal to E. And now we've got a pattern match on C. And a pattern match on S2 underscore 1. So let's destruct that. And now a pattern match on S2 underscore 2. And now we've got a base case. This t is not equal to E. This is going to go on for a while. So let's use proof automation. And I'm going to use really just a kind of proof automation that Adam showed you 2 days ago. So let's do match goal with, I'm going to start each case with a vertical bar. And the first case is, I don't care what's above the line, but below the line, and so I'm using this turnstile to separate the part of the pattern that's for what's above the line from the part of the pattern for what's below the line. If I see an if statement with something, then whatever, else whatever, not equal to whatever, then what should we do? Let's destruct A.
Did you have a syntax editor?
I don't know. No? Okay, so I want to destruct that LTB-XK. How do I know that that's what I want to put in my proof automation? Because in the proof I was doing by hand, that's what I did. And it seemed like I was making progress. So I'm just automating the thing I had been doing by hand. All right. Now, let's see. I want to add another case to this automator to if the goal is match something with red arrow whatever and black arrow whatever, then end is not equal to whatever, right? That's what I had below the line. And now this arrow is not part of what's below the line. It's the separator for my LTAC match clause. In that case, I want to destruct A. Okay, so that's the second clause. And of course, I'm going to put a repeat here so that it, keeps doing this pattern match as long as it keeps working. Why is this not? There is. Okay, so now I've got 5 cases. And one of these cases is solvable by t not equal to e. So maybe I should put a clause in my match that says, whatever your goal is, put an underscore there, try apply t not equal to e. Turn off my own phone too. Okay, so here we go. And now there's only 2 cases left. So of those 5 cases, 3 of them were knocked off by t not equal to e. And what have we got here? We've got a pattern match on, not on red and black, but on E and T. So let's write one of those. We're going to say if the goal is match whatever with E arrow whatever, and whatever goes to whatever, not equal to whatever, destruct A. Bingo. All right, so let's take away, just for fun, this clause. There were 117 subgoals, 117 cases in this case analysis. So you could keep typing them by hand. You could use that proof automation known as cut and paste, which is quite effective. But really, this kind of tactic automation is very useful when you have proofs by case analysis. And once the tactic is all written, it looks like you really knew what you were doing and it's magic. But as you see, I developed it line by line from a smaller one to one with more lines as we began to see what kind of cases show up and what to do about them. I also took care to limit the applicability of the cases, right? So here I applied T unique E because there was a particular pattern of case and I wanted to only match that case, right? And so I don't want these pattern matches to be powerful and out of control. I want to say there are certain cases that I expect to appear. Let's just do those. In other contexts, I do want fancy schmancy, proof automation pattern matches that do stuff I don't even know what it is they're doing, but they get the proof done. But here, really, let's be disciplined about this and match the specific cases that we know are appearing in this proof.
Well, would you consider just for educational purposes showing us the much shorter version of this that also works? We can strictly delete content from the current tactic and it keeps working.
We could delete content from this tactic.
You just need one pattern for any kind of match, and an if is a match too.
Okay, so it's sort of match A with.
Yep.
Yeah, okay. All right. Now, let's review the search tree property. Well, the search tree prime property for red-black trees is identical to what it was for ordinary search trees, except that there's some colors in there that it ignores. So, done. And search tree without a prime is the same, so done. And now let's prove that balance applied to a tree T is a search tree. Now, balance did all those rotations. So this theorem, remember what balance does? Where am I? Right here. This is like a capital T. Think of balance as a capital T, but with some local rotations. And by saying that balance is a search tree, I'm really proving that these rotations preserve the search tree property. So this is a non-trivial theorem. So the premises are, well, much like the premises of insert search tree in the ordinary case, right? That I had to say, if the left subtree is a search tree between low and k, and the right subtree is a search tree between k plus 1 and high, then when I build T with left subtree S1 and right subtree S2 and k is the key, then that thing is a search tree. That was the old theorem. The new theorem is, and if I rebalance it, it's still a search tree. Okay, so let's see how this is proved. Unfold balance. So this is what we have to prove. Okay, so let's see if we can prove it by stupid case analysis. And so I'll start by case analysis on colors. That's this line. And case analysis on tree nodes, E or T. That's that line. And I could do this one at a time, but I think you get the idea. So now there are 58 cases. All right. And how do we prove these cases? Well, the first case, I'm going to hope that this works. There's a search tree prime constructor for T. And so let's just apply it. So constructor, and it has some premises, but they're solved by auto, because the premises it needs are exactly H and H0. Okay? So that was case 1. Here's case 2. Well, case 2 is just like case 1, except with a black instead of a red. So it's not too surprising that it works. Case 3 is this one. I've got a nested tree, but actually its right subtree is already described as a search tree by H0. So constructor auto just works. Then in the next case, I do constructor auto, but it leaves some subgoals. So the first subgoal, we could analyze it, or we could just hope. Let's hope. Constructor auto. Well, it simplified it down, so we could analyze this or just type. So let's just type. And it simplified that down. And now we could have gone into a dead end to get to an unprovable goal, but let's look at this goal and see how it can be proved. We need to prove that k plus 1 is less than or equal to k0. Why would k plus 1 be less than or equal to k0? Well, over here on the right, there's a k plus 1 in a search tree prime with a k0 over there. And we know that search tree prime has some properties about keeping its keys in order. So how could we take apart that search tree prime H0 to get those ordering properties? By inversion of the search tree prime property. Remember, that's an inductive proposition, and if you invert it, you get its premises. So inv H, I'm going to do inv H. Look at H. H is about low and k. And so by inverting search tree prime there, I get that low is less than or equal to k. That's useless, but I'm going to do it anyway. right? So now H1 is what used to be H, but sort of the inverted version of it. Now let's invert H0. And remember, inv deletes H0 after inverting it, because I've extracted all the information I want out of H0, and I don't want extra search tree prime premises hanging around after I've extracted the useful information out of them. Let's, now that we've got the hang of this, rather than thinking, let's just invert every search tree prime premise in sight. So invert H8, invert H9, and by now, look at the premise H. It says k plus 1 is less than or equal to k0. That's what we wanted. So we can solve this by auto. All right, now more of the same. I'm going to apply the search tree prime constructor, and now invert every search tree prime thing I can find, and eventually I can solve it by auto. So let's add that pattern into the repeat match goal. So step 1, see if you can do constructor auto. So no matter what the goal is, see if you can solve it with constructor auto. Let me say that more accurately. See if constructor does actually apply. May not solve the whole goal, but if constructor can apply, apply it. All right, there were 58 cases before. Now there are 70 cases. Is that progress? Yes. Okay. Now, look at this case. It's the thing where we had some search tree primes above the line, and we want to invert them. So let's add a case to the match goal. It says if there's a thing above the line, it doesn't have to be named H. H is a sort of binder for whatever it happens to be named. And it has the form search tree prime, whatever. And below the line, I don't care what we have. Then invert H and clear it, because we don't want the old one to match this pattern again. Okay? So let's see what happens. It's infinite looping. So let's kill that infinite loop before some even worse thing happens. And let's be more conservative about what we match. Let's say the node here has to actually be an E or a T. Because if you look at what we have now in H and H0, we have an S1 and an S2. And when it's a variable rather than actual concrete leaf or node, then inverting H or H0 isn't going to do any good. It'll just leave you with a copy of H or H0. It'll be named something else. Then you'll delete the original, and this rule will match again, having done nothing useful. So we need to narrow down this case to something that's a base case. So I'm going to put an E here, and another copy of it with a T. And then I have to remember how many, 1, 2, 3, 4, 5. Okay. So now there's still 70 cases. Something didn't work. What didn't work?
Do you need constructor without auto?
No, auto never does any harm. If auto can't do anything, it doesn't complain. It just doesn't do anything.
But in the cases below, you're not calling constructor.
Well, yeah, but then the repeat match goal will come around to the top and call constructor again.
Try moving the last two to the beginning.
Ah, yes. Okay. You think? The very beginning, or?
Constructor too early before you get the inversions, and then you never give auto a chance to run later, because constructor doesn't apply in that case.
Ah, right. So maybe we just want, so that, what you described could work, but we could just do this, which is a typical way to do things. And we don't even need the auto here. Bingo.
This might be a lot slower than the way I
Oh, yeah? Okay. So, where are we? That was it. Now, what Adam said 2 days ago was, when you look at this proof, you can see what the cases are in the case analysis. So let's look and see if we can read this match. And it says, well, do the last 2 lines say, do case analysis. No, let me get this right. Right. The problem with having an ultra high resolution display on this stupid operating system with this stupid IDE is that you can't see the cursor because it's made out of pixels, and you know, pixels are so 20th century. Okay, now this says if you have proving search tree prime on a case that's matches, you know, a color. Now, where does a Galena term of match on a color come from? It comes from the definition of balance. So we're taking apart that. Let's look again at the definition of balance. Right? It's the match RB. So we do case analysis on that kind of thing. And there's another match on balance, match T1 with either a T, right, or not a T, right? And then there's a match T2 with either a T or an E, right? And of course, what's written here as a simple 4-clause pattern match really expands to lots of primitive case analysis in Galena. As I showed you, there were, you know, that big term. So in this proof automation, you can see the kinds of case analysis that's necessary to do, and then the kinds of inversion that it's necessary to do. And I claim there's really only 6 kinds of things to do in this proof. Number 1 is auto, where some assumption about less than has proved your goal. Number 2 is apply the search tree prime constructor. Number 3 is case analysis on red or black. Number 4 is case analysis on E or T. Number 6, or whatever it is that I'm up to now, is inversion of the search tree property on the empty tree. And finally, inversion on the search tree property on a non-empty tree. And it wouldn't shock me if this one is unnecessary. But it is necessary, apparently, in these cases. So let's put it back. All right. So now that's proved. Do we understand why balance works? Who during my presentation of balance looked closely enough at what it's doing to actually understand its rotations in detail? Raise your hand. I'm not even raising my hand. Okay. I'm trusting Chris Okazaki. But as we know, doveriai no proveriai, trust but verify. So now we did the verification, but no, we didn't do the verification. Coq did the verification. We just suggested Coq some hints about how to do the verification in proof automation. So that's what case analysis looks like in Coq. Now you have some exercises. So I invite you to prove, well, this one is actually quite easy, that ints is a search tree, because the heavy lifting has been done in the proof that balance is a search tree, and what inst does is is go left and call balance, or go right and call balance, or I'm right here and I don't even need to call balance. So if you look at your proof from the ordinary search trees and you paste it in here and you call the balanced search tree lemma, it should be easy. Okay.
Can I make one more comment before we scroll too far?
Sure.
Repeat match loop.
Yep.
I think especially if we generalize this to imagining larger goals, then moving those last two cases of the match to the beginning should make things significantly faster, because the way things are now, if you keep using constructor to split one goal into many, you repeat the inversions for every sub-goal separately. And so you'll pay that cost over and over again, where you can pay it less frequently.
Okay, so Adam says, and I'm going to argue with him, that by doing the inversion first, you get the benefit of that inversion over all the case splits you're about to do of red and black and E and T. And that's generally true, but in this case it might also be true that in some of those cases of red and black and E and T, you didn't need to do those inversions. So it's not guaranteed that it would be faster by rearranging the terms, but it might be. And these 117 cases are peanuts compared to the kind of case analyses you might get in big systems, where it really begins to matter how slow your proofs are. And in particular, this nice short LTAC generates a very big proof term in Coq that QED now has to deal with, right? So it can start to matter. Okay. So we have our abstraction relation. We have various exercises for you to do. In some of these exercises, you may run into a bunch of cases, and you will need to use exactly this style of proof automation, carefully expanding the clauses of your repeat match to handle the cases you see. And here's my recipe. So let me widen this. Here's an example of an exercise. We want to prove that if some tree T satisfies the abstraction relation with a map M, then the rebalancing of that T will also satisfy the same abstraction relation. Okay? This is not surprising that you might have to prove such a thing in a proof about red-black trees. And so how does the proof go? Intros, inversion H, unfold balance. Okay. Repeat match goal with, whatever. Let's see. So here's the thing we need to prove. It's the usual kind of case analysis. This time the context is in this abs relation. And in the comments, I give you suggestions about what clauses to add. So this thing in yellow here is what in LaTeX would be called a proof. Okay? It's a description, right? The short version of this proof is theorem. If a tree satisfies the abstraction relation, then the rebalance of that tree satisfies the abstraction relation. So proof number one, by case analysis, QED. Okay? Proof number two, by the following case analysis. And, I'm describing this case analysis here in terms that are slightly Coq-ish, but, whenever an abstraction relation with an empty tree is above the line, invert it. Whenever an abstraction with a concrete internal node T is above the line, invert it. And then whenever you have the search tree property above the line of an empty node, invert that search tree property. And then the same for search tree properties of internal nodes. Now I'm up to number 5. Whenever you have abstraction on a program that tests a color, do case analysis on the color. Whenever your program does case analysis on whether a node is a leaf or not, do case analysis on whether the node is a leaf or not, and so on and so on. There are 12 different kinds of things you need to do in this proof. 12 is a lot, but it's better than 178, which is approximately the number of different cases there are in the actual case analysis of the underlying data structure. So that's what this kind of proof automation gets you. All right.
Comment on that outline?
Yeah.
I think that this is an opportunity for me to point to this as the justification for some things I introduced without saying enough about why they were in the proofs I was showing. We can definitely cut this list in half by, for instance, not every place where it says, look for invert with an E, look for invert with a T. That's where the invert one tactic that I showed would work well, which says do inversion if it leaves exactly one sub-goal. You can just say, look for the abs relation with any arguments and try invert one. If you get one sub-goal left, then it was one of the two cases that's currently explicitly enumerated here.
Okay, so Adam is explaining that on Monday he showed this invert one tactic and an invert two tactic and so on. And this is a general way to limit what kinds of inversions you're doing. And by using invert one, that might cover several of these different cases all in one line. I'm a little unsure about invert one, though, because if I invert abs where the thing is a variable, it will still only leave one subgoal because it won't have done anything.
Don't you get two sub-goals? Does abs have one constructor or two?
I can't remember. But there were cases I showed earlier in this lecture where, yeah. All right, so some of the programming techniques for LTAC that Adam showed will cover several of these instructions in one case that's said concisely rather than doing them out so explicitly as I've done here. Okay, I'm about done. We can do this for elements as well. If you do this homework, which I encourage you to do, first do the ordinary searchtree.v homework, because all the principles from searchtree.v will apply here. Several of them just paste in directly with almost no edits, and they work. And in others, you need to call one of these lemmas about balance. All right, so that's how you prove that red-black trees correctly implement the abstract data type of maps. Now, are they efficient? Red-black trees are supposed to be more efficient because they stay balanced. Now, let me back up a little. What's the representation invariant for a red-black tree? Well, it is a search tree. But also, you can't have two red nodes in a row. And the number of black nodes on a path from the root to any leaf must be the same. What if you had a tree that satisfied the is search tree property but didn't satisfy the is a red-black property, right? Then you could still prove it correctly implements functional maps. It's just it might not be balanced. I mean, the amazing thing about Okasaki's program was that you can prove that it's correct with respect to the results it returns without even maintaining the invariant of the red-black property. That's strange, but what it means is that all that rebalancing preserves the search tree property even if it was rebalancing the wrong way to make the trees more unbalanced. Okay, and the lookup will still work. But we would like to know that the trees stay balanced for efficiency purposes. Now, we don't have a formal machine-checked cost model of the execution speed of Galena functions. We're going to reason informally about the speed of our programs In other words, what in the 20th century would be called a proof. Okay? But what we can prove in Coq is that the height of the tree is bounded by 2 log n. And we do that in these steps. So the remainder of this file from this exercise 4 onward is in support of a half machine-checked proof about the time cost of running red-black trees. Number one, it satisfies the is-red-black property. So is-red-black takes a natural number that's going to be the number of black nodes on every path from the leaf to the root. And it enforces that, and it enforces there's no 2 red nodes in a row, and so on. And then we prove that if you insert, here we are, if a tree S is a red-black tree with n nodes on n black nodes on every path from the leaf to the root, and you insert X into that tree, then the resulting tree is also a red-black tree, and there is some n prime, which is usually equal to n, but might be 1 higher, that characterizes the number of black nodes on every path. And from knowing the red-black tree property, you could then prove that the height of the tree is bounded by 2 log n. And you could do that in Coq, and it wouldn't be that hard. I haven't put it in the exercises here. And now half of your proof about the efficiency of your program is already machine-checked, even though we have no formal cost model for the other half of the proof. Okay, so that's that. And now let's... Yes?
So looking at the inductive definition for is-red-black, I'm not seeing something that says that leaves have black, which was part of your informal...
Well, yes, the question is, where does this inductive definition is red-black say that the leaves are black? Okay, and the leaves aren't explicitly marked with a color, but if every path from the root to a leaf contains exactly 1 leaf, so whatever color we assume the leaves to be won't interfere with the property that every path has the same number of black nodes. We do sort of need to have the leaves assumed to be black because the node right above them is permitted to be red. All right? But it doesn't have to say so explicitly for this all to work. Okay. So let me, stupid Windows. It's made it tiny again. All right. So here was search trees. No, here was search trees. Ordinary search trees without balance. So 1 million random integers to insert and look up took 1.344 seconds. 20,000 random integers took 0.016 seconds. And 20,000 consecutive integers took 5.296 seconds. And when we do red-black trees, we get this. So 1 million random integers is 1.156 seconds. And 20,000 consecutive integers is just as fast as 20,000 random integers. It's slightly faster, but I assume that's a coincidence. What's interesting is even the random tree, the 1.156 seconds for the random tree is better than the ordinary search trees. So even random trees are, slightly imbalanced. And the extra cost of looking at colors and rebalancing trees even improves the runtime for random trees. And it vastly, what's 2.5 orders of magnitude improvement on the 20,000 consecutive integers. Okay, so questions about red-black trees? Okay. When you do program verification, you don't always need to be afraid of horrible case analyses. We should strive to do our proofs without horrible case analyses, but when they pop up, no big deal. Now, next, let's talk about arrays. Should we take a break for 3 minutes first, or just finish up and get to lunch? Raise your hand if you want to break now for a couple of minutes. Raise your hand if you'd rather finish up and get to lunch. Okay. So, in imperative programming languages, you have arrays with constant time access. And here's a little program I could write in C that, tests whether in the input, in the n integers of input, each input value in the range from 0 to 2n, there are any collisions. So we will just make an array A indexed by the values of these integers, and we'll initialize that array all to 0. So that's the first loop. And then for every I in the input, so j is the index into the input array, but I is the input value in the next loop, if we will set a sub I to 1, but first we'll check whether a sub I was already 1, and if so, we found a collision. Okay, everybody happy with that program? It detects how many collisions there are in n different integers, or n integers, all in the range 0 to 2n. And how fast does it run asymptotically? Linear time. It's got a couple of for loops in it, and one of the for loops has an if statement in it. The asymptotic analysis of this is not hard. Okay? So that's good. In a functional program, well, we don't have arrays with constant time access generally, because in a functional programming language, we can't mutate old values. Some other part of the program might still be pointing at that old value and expects it to continue to have that value, right? So we would have to create a new array, just like the old array, except different at one slot. And that would take linear time just for that one operation, that one update, and we certainly don't want to do that. So we generally don't have arrays at all in these functional programming languages like, Galena or Haskell. And, you could play around with state monads, but that's sort of outside the system. And the thing about our pure functional programs in Galena is that we need to prove them correct. We don't really want to step outside the system and complicate the proof theory of the surrounding logic. So what do we do instead? We have efficient functional maps, right? If our integer values belong to some totally ordered type, for example, we could use red-black trees to implement that array and do a functional update of the tree and pay a log n penalty, because every update costs log n instead of constant time, and every access costs log n instead of constant time. We can basically run these loops, but every subscript is a log n operation, and the whole thing takes n log n. So that's where we're going to go here, except there's some twists. So let's start with this program in Coq. It takes an input that's a list of nat, It takes a C, which is how many iterations, or it's the count of how many collisions there have been. It takes a table, which is a recording of which integers we've seen so far. That's a total map from the Software Foundations map library. And it maps each natural number to a Boolean, saying whether we've seen it before. And so what do? If the input is nil, we're done. We report the number of collisions. If it's a number A, then we look up that ID of A in the table. If it's already there, we loop again with C plus 1 because we found another collision. If it's not already there, we update the table to true at that location. And we didn't find a collision this time, so we use C again. And collisions just runs that loop with 0 and the empty map. Okay, so the number of collisions in this array 3, 1, 4, 1, 5, 9, 2, 6 is 1 by reflexivity. Okay, and how fast does it run? Well, it takes n cubed time. N cubed, that's pretty bad. Where does n cubed come from? Well, each operation, well, there are n iterations. That's the first n. Then each operation on a functional map takes, what is this? Let's see. Look at the line, if table, right here. That's a lookup in this table. And that lookup goes, if it's equal to this one, else if it's equal to that one, else if it's equal to that one. And on the average, it may get halfway down the list. So that's linear time in the size of the table. All right, so that's our second factor of n. And our third factor of n is we're using NAT. So each comparison that it does in each of those if statements is a comparison on natural numbers, and that takes time proportional to the size of the natural number. So that's very bad. N cubed. Let's use the integers. And I explained to you the positive type and the z type and their representations in my first lecture. And so I'll skip over all the details, but it's there in the file if you want to play with the integer representation. Here's the case analysis for adding positive numbers with carry. This looks bad, but it has to run only log n times because the length of the representation is really log n. And I think it's worth at least reminding you what the representation is, that xh means 1, such that we could even write an interpretation function positive to nat that says, well, if you see xh, then it means 1. And xo of q means 0 plus 2 times whatever q means. And xi of q means 1 plus 2 times whatever q means. So it's this data structure. You get xi of xo of xo of xi of xo, and eventually it terminates with an xh. And you can read it, the o's and i's, suggestively named as 0 and 1 bits in the binary representation, except backwards. All right. So now if we do the same loop, here's the same loop again. Total map z is a map on calc integers rather than nat, and it looks a lot like total map did. It's still got that same if statement in the update function, right? So how fast does this program run? Well, we've taken one of the factors of n and replaced it by a factor of log n. So instead of running in n cubed, this runs in n squared log n. This is a great improvement. Okay? Everybody with me? All right. Now let's replace that total map Z, with balanced binary search trees. Okay? And so now it's exactly the same loop, except that this is a lookup in a balanced binary search tree, and that's an update, an insert in a balanced binary search tree. And now that update, how long does it take? How long does this lookup take? Well, it's doing log n comparisons. Comparison of a z takes log n time in the value of the z, because the binary representation has log n bits in it, and you may have to walk down those log n bits to find if one is different. Okay? So update or lookup in a red-black tree on z will take log squared n time. That's not bad, but it's a little disappointing. So now our loop takes n log squared n time. And remember, the C program took linear time. So what do we do about this extra factor of log n? The answer is don't use red-black trees. And the trick is we're going to use a balanced tree data structure that operates directly on the bits of the number. So now I'm going to do this for positive numbers instead of for z, just to make things clearer. We don't need that sign bit gumming things up. Imagine a tree where I'm going to index on the bits of the binary number. If it's a 1-bit, go right. If it's a 0-bit, go left. If you reach the end, stop, and that's where you are in the tree, and that's where you've stored the value. Okay? So that's called a trie, T-R-I-E. In general, a trie is on any alphabet, for strings on any alphabet, right? So if you had a 26-letter alphabet, then each node in the tree would have 26 children, and they would be, of course, indexed by what letter you have here. Therefore, a trie is really a kind of finite state machine. It's a recognizer. Okay? But these are binary tries. And they're in the Calc library. They're called P trees, capital P, for positive. They're trees indexed by positive numbers, and positive in this particular efficient binary representation. They're in the Calc library because a dozen years ago they were in CompCert. Lois and Blazy, when they were implementing CompCert, noticed that they have to look up variable names, identifiers, register numbers, all the time. There are all these positive numbers, and not really huge positive numbers like, 10 to the 8th, just positive numbers proportional in value to how many different identifiers you have in your program, a couple of thousand. So their binary representation is only maybe 10 long. And so they implemented binary tries as lookup tables. And how do they work? Well, here's the lookup function in a binary trie. We're going to look up the positive number I in the trie M. Oh, I should show you what the trie is. A trie is either a leaf or it's a node. And we don't need a key at this node. It doesn't work like that. But we do need the value, the binding, the value we've stored that corresponds to the binary number whose bits have just run out right here on our path down from the root. And then we have a left subtree in case there are more bits and the next one is a 0. And there's a right subtree in case there are more bits and the next one is a 1. Okay, so that's a trie. And here's lookup in the trie. If you're looking up I in M and you reach a leaf before you run out of bits, what does that mean? It means that nobody ever inserted this value in the tree before, so you should use the default value. Okay? But otherwise, we have a node, and now we check what bit our number starts with. Now remember, starts with is if you're reading it backwards, right? So is this, it's more like, what does it end with? And xh means there's no more number here. Okay? So we've reached the end of our bits, and this node in the tree is where we've stored some value and returned that value x that we found right here in that node of the tree. Otherwise, if we have xo, we will, with the remainder of the bits being I prime, we will look in the left subtree with the string I prime. And similarly for the right subtree. So this fixed point is structurally recursive, as it must be to be a fixed point in Coq. And that's a proof that it terminates, as it always is in Coq. But in particular, it's a proof that it terminates, in proportion to the thing it's doing structural recursion on, which is the number I. Okay, well, actually, this is structurally recursive both on the depth of the tree and on I. We could choose, I think, whether I or M is our struct thing. And I could enforce that by putting struct I in braces. But here we're using a piece of Coq's logic, when is a fixed point accepted by the system, as a kind of machine-checked proof that this is efficient, that it terminates in time proportional to the number of bits. Okay, so now here's our loop. Same loop as always. It's just now we've got lookup a table, and we've got insert a true table instead of what we had before. Otherwise, it's identical, and it runs in n log n time. Now, when you program in imperative languages, shall I say, when you programmed in imperative languages back in the 20th century or whatever, you used arrays indexed by integers a whole lot. And when we program in pure functional programming languages, we're going to use lookup tables indexed by integers a whole lot. And this is the one to use, this P-tree data structure. Is there anything more I want to say about that? Right. So you can find it in the positive map module, which implements the fmaps interface in the Coq library. Okay. And I think, yeah, let me say a few more things about balanced trees. Suppose you want priority queues. And here are the operations you might want on priority queues. Create a priority queue, insert an element into a priority queue, find the largest element, or sometimes it's the smallest element, but you only get one. So let's say find the largest element, return its value, and delete it from the queue. So those are the standard operations on heaps. So who has seen the heap data structure with these operations and log n performance? Now, I want two more operations. I want to be able to merge two queues together, so the sort of union of the two sets. And I want persistence. I want my program to be able to put its finger on one state of a priority queue and sort of put its finger on another copy of the priority queue and start updating this one without losing the value of this one. Okay? So let's see. How would we do this? Well, one way is to use red-black trees. How expensive are these operations on red-black trees? Create is easy, constant time. Insert is log n. Find the max is you just walk down to the right of the tree, and the rightmost leaf is the maximum element. So it's log n to find it, it's log n to delete it and rebalance the tree as necessary. So delete max is log n. Okay. How do we join two red-black trees? Well, it's not so easy. If one tree is smaller than the other, we could insert all the elements of the smaller tree into the bigger tree, and that would cost log of the size of the bigger tree times the number of elements in the smaller tree. But that's sort of n log n in the worst case, when they're about equal. So here's another way. We could flatten both trees into lists, and you can flatten a binary search tree into a sorted list in linear time, as I showed you. And then I can merge two sorted lists together. That takes linear time. And then I can rebuild a balanced tree out of a sorted list in linear time, as I did not show you, but as is true. And so that means that you can do join in linear time. That's better than n log n, but we were hoping for, I don't know, what were we hoping for? Log n? Probably. And then persistence. Well, we're programming in a pure functional language. Persistence is like easy. It's the default. So we're already in good shape with balanced binary search trees, but we would like to do better. So there's this algorithm called binary heaps, or there's an algorithm called binomial queues or binomial heaps. It dates from about 1978. And it's easily implemented as a pure functional data structure. I don't really have time to show you its cool properties, but yeah, I'll just remark those claims I made about what you can do with binary search trees, about constructing trees in linear time from flattened lists and inserting the smaller one into the bigger one or the bigger one or whatever. You can see a tech report I wrote. But you don't have to see the tech report. You can just use it. It's in the Coq library, coq.msets.msetRBT. Has all the usual operations on red-black trees, plus delete min for use as a priority queue, plus union and intersection, right? You can use these as sets for your functional programs, and they will run fast. Okay, so here are the properties of binomial queues. Insert is log n, delete max is log n, join is log n. Right? And so it's a fun tree data structure. You can get the appropriate chapter of Sedgwick's book from this link, which is linked. You can find this URL in the binomial queues chapter of verified functional algorithms. And it explains, well, these pictures on the slides are actually stolen from Sedgwick's book. So it's a fun data structure, and if you ever want to play around with inductive proofs about balanced trees for another purpose, there it is. And I will stop here. This ends my 3-lecture series on verified functional algorithms, and on Friday I will talk about verified imperative programs.